Good morning, everyone, and welcome. I'm Vandana S., and I'm excited to start this presentation with you today. We'll be exploring radiation quantities and units, a fundamental aspect of radiological physics. This session is part of the Radiological Physics and Advisory Division's efforts to deepen our understanding of radiation measurement. Over the next few slides, we'll cover key concepts, important units, and how we quantify radiation in various contexts. Let's get started and make this an engaging learning experience. Quantities are fundamental when we want to describe physical phenomena in a precise way. They help us quantify things we observe or measure. Now, a unit is essentially a reference sample we choose for a particular quantity, so we can compare other measurements to it. Think of it as a standard or benchmark. Every physical quantity can be expressed as a combination of two parts, a numerical value and a unit. The numerical value tells us how much of the quantity we have, while the unit provides the context or scale for that number. This relationship is crucial because it allows us to communicate measurements clearly and consistently. When we talk about quantities and units, we're establishing a common language that ensures everyone understands the magnitude and scale of what we're measuring. This concept ties into our overall theme of understanding how to accurately measure and describe the physical world around us. Let's start with the term radiometric. This describes the field of radiation itself, essentially how we measure and understand radiation in a scientific context. It's about quantifying the radiation that we're dealing with. Next, we have interaction, which refers to the moment when radiation interacts with matter. This is a crucial point because these interactions determine how energy is transferred and how biological tissues might be affected. Moving on to dosimetric, this relates to the energy depositions in matter. Basically, it's about measuring how much energy from radiation is deposited into a substance, which is fundamental for assessing potential effects or risks. Finally, protection involves folding biological response functions into dosimetric quantities. This means we incorporate how living organisms respond to radiation into our measurements, enabling us to better evaluate and manage radiation safety. Connecting all these points, the sequence of quantities, from measuring radiation itself, understanding how it interacts, quantifying energy depositions, and finally considering biological responses, provides a comprehensive framework for radiation protection and assessment. This progression is key to ensuring we understand and mitigate radiation risks effectively. Let's take a moment to look at the roles of two key organizations in the field of radiation measurement and protection. First, we have the International Commission on Radiation Units and Measurements, or ICRU. Their main goal is to develop standardized quantities and units for radiation and radioactivity. They also establish procedures for measuring these quantities and ensure that these standards are applied consistently across various fields, including radiology, radiation therapy, radiation biology, and industrial operations. This helps us achieve accurate measurements and safe practices worldwide. Now, moving on to the International Commission on Radiological Protection, or ICRP. Unlike the ICRU, which focuses on measurement standards, the ICRP serves as an advisory body. Their primary role is to provide recommendations and guidance on protecting people from ionizing radiation. Their work helps shape safety protocols and regulatory limits, ensuring that radiation exposure is kept within safe levels. Together, these organizations play crucial roles in advancing our understanding of radiation, ensuring accurate measurements, and promoting effective protection measures. They are integral to the overall theme of this presentation, which is about understanding and managing radiation safely and effectively. Let's take a moment to discuss the concept of the radiation field. When we talk about a radiation field, we're referring to the spatial distribution of radiation intensity within a given area. It's essentially how the radiation spreads out and varies across different regions. This is a crucial aspect because understanding the radiation field helps us determine the exposure levels at various points, which is vital for safety and effectiveness. The key points here include recognizing that the radiation field isn't uniform. It can be influenced by factors like the source strength, distance, and any intervening materials. By analyzing the radiation field, we can optimize our setup to ensure precise delivery of radiation while minimizing unnecessary exposure. This ties directly into our overall goal of achieving targeted, controlled radiation treatment or measurement, ensuring safety and accuracy throughout the process. Let's start by looking at how we can quantify a radiation field. One fundamental quantity is the fluence, denoted as. This represents the number of particles that strike a small area, which we imagine as a sphere with cross-sectional area dA. Essentially, it tells us how many particles are incident on that area. Mathematically, it's expressed as dN divided by dA, and its unit is per square meter, or m2. Moving on, we have the energy fluence, symbolized as. This measures the total energy carried by these rays that hit an infinitesimal sphere of area dA. If we think about R as the energy per particle, R equals E times N, where E is the energy of each particle. So the energy fluence equals E times the fluence. Its unit is joules per square meter, Jm2. Next, we consider how quickly these quantities change over time. The fluence rate is simply the derivative of fluence with respect to time, d/dt. Similarly, the energy fluence rate is the rate at which energy passes through, or strikes, the area, which is d/dt. Finally, these concepts fall under what we call radiometric quantities. They are essential because they help us characterize the intensity and energy distribution of radiation fields, which is crucial for understanding how radiation interacts with matter and for designing appropriate detection and shielding systems. Interaction processes occur between radiation and matter. In an interaction, the energy or the direction, or sometimes both, of the incident particle can change, or the particle can be absorbed completely. The key idea here is that these interactions are what cause attenuation of radiation as it passes through material. Now, to quantify this, we use the linear attenuation coefficient, represented by the symbol micro. Think of micro as a measure of how much a material reduces the intensity of radiation per unit length. It tells us the fractional attenuation that occurs over a small distance. Specifically, the probability that, at normal incidence, a particle will undergo an interaction within a tiny layer of material, of thickness dl, is proportional to d micro. But since materials vary in density, and that affects how they attenuate radiation, we often refer to the mass attenuation coefficient, which is micro divided by rho, the density of the material. This way, we essentially normalize the attenuation by mass rather than just length, making it easier to compare different materials regardless of their density. Understanding these interaction coefficients helps us predict how radiation behaves as it moves through various substances. It's fundamental to designing shielding, imaging, and many other applications involving radiation safety and effectiveness. Let's take a closer look at this key relationship. LAC, or linear attenuation coefficient, is equal to the MAC, or mass attenuation coefficient, multiplied by the density of the material. This means that the overall attenuation depends both on the material's inherent properties, represented by the MAC, and how densely it is packed. Now, the relationship between MAC and LAC is fundamental because MAC is a normalized value, per unit mass, while LAC accounts for the material's density, giving us a practical measure of how much intensity is reduced as the radiation travels through a specific thickness. We also see the concept of HVL, or half-value layer, which is the thickness of material needed to reduce the initial intensity by half. The equation involving the natural logarithm of 2 comes into play here, showing how we calculate HVL based on the LAC. Remember, the equations like I equals IO e to the minus mu describe the exponential decay of intensity as radiation passes through material. When equals HVL, the intensity drops to half of its original value, which is a key point for understanding shielding effectiveness. Finally, it's important to note that both mu, the attenuation coefficients, and HVL depend on the energy of the photon radiation and the properties of the material itself. So, as energy changes, these values will change too, affecting how we design shielding and assess radiation exposure. Now, let's look at how radiation interacts with matter and what factors influence this process. The effect of radiation depends primarily on two things. First, the radiation field itself, which is described by radiometric quantities. These quantities tell us about the intensity and distribution of the radiation. Second, it depends on how radiation interacts with the matter, which we characterize using interaction quantities. These detail how likely it is for radiation to interact with tissue or other materials, and what kind of interactions occur. To understand the actual biological or physical effects, we use dosimetric quantities. These are really important because they give us a physical measure that we can relate directly to potential effects, like damage or dose absorption. In essence, dosimetric quantities are products of the radiometric quantities and the interaction coefficients. This means they combine the properties of the radiation itself with how that radiation interacts with matter, giving us a clearer picture of what's happening at a more practical level. So, in summary, understanding these quantities helps us to predict and quantify the effects of radiation, which ties back into our overall goal of managing radiation exposure safely and effectively. Let's talk about the quantity of radioactive material. This refers to the number of disintegrations or transformations that occur per unit time. In other words, it's a measure of how active the source is. The more disintegrations happening each second, the higher the activity. Now, an important point to remember is that the amount of radiation released, or its intensity, is directly proportional to this activity. So, if the activity increases, the radiation intensity also increases, and vice versa. And because radioactive materials decay over time, their activity doesn't stay constant. It gradually reduces as time passes. This means that the intensity of radiation emitted from a source diminishes as well. Understanding this relationship helps us grasp how radioactive sources behave and how their hazards decrease over time, which is crucial for safety and measurement purposes. Let's take a closer look at some common units of radioactivity measurement. Starting with the conversions, 1 kilocurie, or 1 kci, equals 10 to the power of 3 curie, which is written as 10^3 Ci. Similarly, 1 kilobecquerel, or 1 kBq, also equals 10^3 becquerel, so 10^3 BQ. Moving up in scale, 1 megacurie, or 1 MBq, is 10^6 becquerel, and 1 gigacurie, or 1 GBq, is 10^9 becquerel. Now, on the smaller side, 1 microcurie, or 1 μSci, equals 10 to the negative 6, which is 10^6 curie. Meanwhile, 1 millicurie, or 1 MCi, is 10 curie, and that's approximately equal to 37 megabecquerel. It's important to note that the SI unit for radioactivity is the becquerel, abbreviated as BQ, where 1 BQ equals 1 disintegration per second. Historically, the curie was used more commonly, and 1 curie equals 3.7 times 10 to the 10 disintegrations per second, or 3.7 x 10 BQ. Understanding these units and conversions is crucial because they help us quantify radioactivity accurately, whether we're working in medical, environmental, or research settings. They form the foundation for understanding activity levels and ensuring safety when handling radioactive materials. Energy indicates the quality or penetrating power of radiation. When we talk about radiation, a key factor that determines how deeply it can penetrate materials is its energy. Now, to express this energy, we typically use units called electron volts, or EV. These units help us measure the amount of energy carried by individual particles of radiation. For larger energies, we use multiples of EV. For example, 1000 EV is called 1 keV, which stands for kilo-electron volt. And when the energy gets even higher, like in the case of very energetic particles, we use mega-electron volts, or MeV. So, 1000 keV equals 1 MeV. Understanding these units and how they relate is essential because they help us compare the penetrating power of different types of radiation. The higher the energy, the more capable the radiation is of penetrating matter. This concept ties directly into the overall theme of radiation safety and detection, as knowing the energy helps us evaluate potential risks and how to manage them effectively. On this slide, we're looking at a quantity that helps us measure how much ionization is produced in the air by X-ray or gamma-ray radiation. This is important because it gives us a way to quantify the exposure of air to these types of radiation. The key point here is that this measure is defined in a specific way, which we'll get into shortly. The SI unit used for this measurement is the Coulomb per kilogram, or C per kg. This unit essentially tells us how much electric charge, in coulombs, is created in a kilogram of air due to the radiation. Understanding this concept of exposure is crucial because it forms the basis for evaluating radiation doses and their potential effects. It connects to our broader goal of understanding how radiation interacts with matter and how we can quantify that interaction safely and accurately. Now, when we talk about ionization, except in cases of very high energies where bremsstrahlung becomes significant, the ionization in air is essentially equivalent to air kerma. This means that under most conditions, measuring ionization gives us a good idea of the energy transferred from radiation to air, which is important for dosimetry. It's also important to note that the concept of exposure specifically applies to electromagnetic radiation when it interacts with air. So, when we measure exposure, we're looking at how much ionizing radiation, like X-rays or gamma rays, affects the air around us. A key point here is the unit of measurement called the Röntgen, or R1 Röntgen is defined as the amount of radiation that produces an ionization of 2.58 times 10 to the minus 4 coulombs per kilogram of air. This helps us quantify the amount of radiation in a standardized way, making it easier to compare and control exposure levels. Overall, understanding these concepts is fundamental for accurately assessing and managing radiation exposure in medical, industrial, or environmental settings. Let's talk about KERMA, which stands for kinetic energy released per unit mass essentially. It measures how much energy is transferred to charged particles when uncharged particles interact with matter. KERMA is defined through a specific equation, where d-iter represents the sum of the initial kinetic energies of all the charged particles that are liberated by these interactions within a small mass, dm. This means that when an uncharged particle, like a neutron, interacts with matter, it can produce charged particles such as electrons or protons, and the energy these particles carry away is what we're quantifying with KERMA. The unit for KERMA is joules per kilogram, which is also called a gray. The gray is a key measure in radiation physics because it tells us how much energy is deposited in a material, which is crucial for understanding dose and potential biological effects. So, in the context of our broader discussion, KERMA helps us quantify the initial energy transfer in radiation interactions, which is fundamental for evaluating exposure and safety in medical, industrial, and research applications. KERMA is a concept that's mainly useful when we're talking about photons and neutrons in any medium. It's important because it accounts for all the energy transferred to charged particles by the incoming radiation, even if some of that energy isn't deposited right there at the point of interaction. Think of it as a way to measure how much energy is being transferred from the primary radiation, like photons or neutrons, to particles that can cause ionization, such as electrons. So, in essence, KERMA represents this transfer of energy from the incoming radiation to these directly ionizing particles. It's a key concept because it helps us understand the initial energy transfer process, which is fundamental for radiation dose calculations and understanding how radiation interacts with matter. This idea ties into the overall theme of radiation interactions, highlighting how energy moves through different particles and mediums, ultimately leading to ionization and biological effects. Today, I want to talk about the concept of air KERMA, which is also known as Ka. The KERMA in air, Ka, is essentially the amount of energy transferred from ionizing radiation to air per unit mass. It's a fundamental measurement because it helps us understand how much energy is being deposited in the air by radiation. Now, an important point to remember is that exposure, which you might be familiar with, is actually the ionization equivalent of air kerma. In other words, exposure measures how much ionization occurs in the air caused by the radiation, and this is directly related to the air kerma. So, to connect these ideas, air kerma gives us a direct measure of energy transfer, while exposure tells us about the ionization process that results from that energy. Both are crucial in understanding radiation dose and safety. This fundamental concept ties into the overall theme of radiation measurement and safety, helping us quantify and control the amount of radiation energy involved in various medical and industrial applications. Kerma is often described as having two components that are fundamental to understanding energy transfer in radiation physics. The first is collision kerma, or Kc. This refers to the kinetic energy transferred directly to charged particles, which then leads to ionization and excitation. Essentially, it's the energy deposited locally within the medium due to these collisions. The second component is radiative kerma, or Kr. This involves kinetic energy transferred to charged particles that is then carried away by photons, specifically through Bremsstrahlung interactions. So, in this case, some of the energy leaves the volume as photons, rather than staying as local energy deposition. When we add these two components together, we get the total kerma, which is simply K equals Kc plus Kr. Understanding these components helps us better interpret how energy is deposited in tissues or other materials during radiation exposure. And this concept is especially relevant when we talk about air kerma, which is a commonly used measure in dosimetry. It gives us an idea of the energy transferred from photons to charged particles in air, helping us assess radiation dose more accurately in various applications. Now let's talk about the exposure, X, which is essentially the ionization equivalent of the collision kerma, Kc, in air, specifically for X and gamma rays. To understand this relationship better, we can express the exposure, X, in relation to the kerma, Kc. The formula is pretty straightforward. X equals Kc in air multiplied by the ratio of the mean energy expended per ion pair, W, which is 34 electron volts, divided by the elementary charge, E. Simplifying that, we get X equals Kc in air divided by 34. This means that if we know the kerma in air, we can directly calculate the exposure. And the key takeaway here is that exposure is measured in coulombs per kilogram, which is a unit of charge per mass. It's important to remember that this relationship helps us connect the physical energy transfer in air, represented by kerma, to the more practical measure of exposure used in radiation protection. Understanding this link allows us to better assess and compare radiation doses across different contexts, reinforcing the overall importance of dose measurement in our field. Now, let's look at how the exposure, denoted as X and measured in coulombs per kilogram, can be related to air kerma. Essentially, this relationship helps us understand how energy is transferred from radiation to air. The formula involves some important factors. W, which is the average energy used by an electron to create an ion pair, and E, the electronic charge. By understanding this relationship, we can better interpret how different radiation quantities are interconnected and how they contribute to dose calculations. This connection is fundamental in ensuring accurate dosimetry and safety in radiation applications. Let's take a closer look at absorbed dose. Denoted as D, this is essentially a measure of how much energy is deposited into matter. The unit we use is the joule per kilogram, or J/kg, which tells us how much energy is being transferred to a specific amount of mass. There's also a special unit called the Gray, abbreviated as J, previously known as the rad. To give you some perspective, 100 rads equal 1 Gray. Now, the key idea here is that the absorbed dose depends on the mean energy imparted to the matter, which means the total energy transferred divided by the mass of the matter involved. Think of it as an average energy transfer per unit mass, giving us a way to quantify the amount of radiation energy absorbed. Understanding this concept is fundamental as it connects to how radiation interacts with matter, which is crucial for assessing potential biological effects and safety measures. So, in summary, the absorbed dose helps us quantify the energy deposited in tissue or other materials, which is essential for our overall understanding of radiation exposure. Let's start by looking at how energy transfer works. The energy imparted to a medium is essentially the difference between the energy incident on it and the energy leaving the mass. This accounts for the energy released during nuclear reactions as well. Now, when we talk about Kerma, we're referring to the transfer of energy from photons to electrons. This is a crucial step because photons transfer their energy to electrons when they interact with the medium. Next, the absorbed dose refers to what happens after that. It's the transfer of energy from these energized electrons to the medium itself, whether that's air, tissue, or another material. So, to recap, Kerma involves the initial energy transfer from photons to electrons, and absorbed dose is about that energy being transferred from electrons to the medium. Both concepts are fundamental in understanding how radiation interacts with matter, and they tie into the overall theme of radiation dose measurement and safety. Let's take a closer look at these key concepts. First, the absorbed dose, which we denote as D, is calculated as the difference between the initial photon energy, hν1, and the energies after interactions, hν2 and hν3, minus T prime or T. Essentially, this represents the energy actually deposited in the material. We can also express it as T minus hν3 and T, showing how the initial energy T is reduced through various interactions. Now, moving on to Kerma, which is a related but distinct concept. Kerma is defined simply as the difference between hν1 and hν2, which equals T. This tells us that Kerma measures the initial transfer of energy from photons to charged particles before any energy is actually deposited. Notice the role of T again here. It represents the energy remaining after some interactions, indicating that not all energy is immediately absorbed. Some is scattered or transmitted. The diagram also shows the volume of material, V, and the photon interactions within it. The electrons, or E, are the primary agents that deposit energy, transforming photon energy into other forms. Overall, these concepts help us understand how energy from photons transfers to tissues or materials, and how we quantify that transfer through dose and Kerma. This understanding is fundamental in radiation physics and dosimetry, linking the microscopic interactions to the macroscopic effects we measure and control. Charged particle equilibrium, or CPE, exists for a specific volume when, for every charged particle that leaves that volume, there is a corresponding charged particle entering it. Essentially, this means the number of charged particles coming in matches the number going out, maintaining a kind of balance. When this equilibrium is present, the dose delivered to the tissue is equal to the Kerma, which is the kinetic energy released per unit mass. This concept is fundamental because it simplifies the calculation of dose in a region where CPE holds true. It's a key part of understanding how radiation interacts with matter and helps us accurately estimate the energy transferred during exposure. So, recognizing when CPE exists allows us to make more precise assessments of dose in treatment planning and radiation protection. Today, we'll be discussing charged particle equilibrium, or CPE, which is a fundamental concept in radiation dosimetry. When we consider depth in a material where there is no attenuation, it means the particles are passing through without losing energy significantly. In this context, Kerma, or kinetic energy released per unit mass, becomes a key measurement. It tells us how much energy is being transferred from the radiation to the material at a specific point. Now, in a state of CPE, the amount of energy being deposited locally, what we call dose, is directly related to the Kerma. Essentially, under these conditions, the energy transferred to the material results in a dose that's equal to the initial energy transfer. This relationship simplifies many calculations because, when equilibrium exists, the kerma and dose are effectively the same. It allows us to make accurate dose measurements in regions where the radiation field is uniform and particles are not being attenuated. So, understanding this balance between kerma and dose at a given depth helps us better grasp how radiation interacts with matter, which is crucial for precise dosimetry and ensuring safe, effective radiation use. Now, let's talk about the protection quantities. These are the measures that are directly linked to the risk of radiation exposure. While we can calculate them under specific exposure conditions, it's important to note that they generally can't be measured directly in routine field situations. Protection quantities include several key concepts, such as the equivalent dose, which helps us understand the biological effect of radiation on different tissues. We also consider radiation weighting factors, which adjust for the different sensitivities of various types of radiation. Then there's the effective dose, which provides an overall measure of risk by accounting for the varying sensitivities of different tissues and organs. Finally, tissue weighting factors are used to give us a way to weigh the contribution of each tissue to the total risk. All these concepts are essential because they help us evaluate and manage radiation protection more accurately, aligning with our overall goal of minimizing exposure risks while understanding the biological impact of radiation. Now, let's look at how we quantify the dose in a specific tissue, which we call the equivalent dose in tissue T. The key formula here is HT equals the sum over all radiation types R of the weighted dose WR multiplied by the absorbed dose DT. R essentially, DT. R is the average dose absorbed by the tissue or organ T from radiation. R, the weighting factor WR, accounts for the relative biological effectiveness of each radiation type R. So, by summing these weighted doses, we get a measure that reflects the overall potential biological impact of different types of radiation on that tissue. This concept is critical because it helps us compare the effects of various radiation sources in a way that's meaningful for assessing risk and planning safety measures across different radiation environments. It ties into the broader theme of understanding how radiation interacts with tissues and how we can quantify those interactions to protect health. In radiological protection, we focus on the concept of absorbed dose, but it's important to understand that we don't just look at the dose in isolation. Instead, we consider the dose averaged over a specific tissue or organ, and we weight that average based on the radiation quality of interest. This helps us better assess the actual biological impact of different types of radiation on the body. The weighting factor used for this purpose is called the radiation weighting factor, or WR. This WR varies depending on the type and energy of the radiation that's incident on the body. For example, alpha particles have a higher WR compared to X-rays or gamma rays because they cause more damage per unit of energy deposited. Finally, when we talk about the unit of equivalent dose, it is measured in joules per kilogram, but it has a special name, the sievert, or SV. This unit helps us quantify the risk of radiation exposure in a way that reflects the biological effect, rather than just the physical energy deposited. Understanding these concepts is crucial because they form the foundation of how we evaluate and manage radiation risks in medical, occupational, and environmental settings. Now, let's talk about the effective dose. The effective dose is essentially the sum of the weighted equivalent doses across all the tissues and organs in the body. It helps us understand the overall risk from radiation exposure. Mathematically, it's given by this formula. E equals the sum over all tissues T of WT times HT. Here, HT stands for the equivalent dose in a specific tissue or organ T, and WT is the tissue weighting factor for that tissue. The key thing to remember is that not all tissues contribute equally to the overall risk, which is why we weight their doses differently. This concept connects to the broader theme of assessing radiation risk comprehensively, considering both the amount of radiation and how different parts of the body respond to it. When we consider the probability of stochastic effects, it's important to recognize that this probability actually depends on which organ or tissue is irradiated. Different tissues have different sensitivities, so their contribution to overall risk varies. This slide shows how we can represent the relative contribution of irradiating each organ or tissue to the total detriment. That is, the overall potential for adverse effects, when the entire body receives a uniform dose. Ideally, if the whole body is uniformly irradiated, the effective dose we calculate should numerically match the uniform equivalent dose. In other words, the measure we use should accurately reflect the biological impact of that dose, regardless of whether the dose is spread evenly or concentrated in specific areas. To achieve this, we normalize the sum of the tissue weighting factors so that they add up to 1. This normalization ensures that our calculations are consistent and that the effective dose truly represents the risk associated with irradiation of different tissues. In essence, tissue weighting factors help us weigh the contribution of each organ's irradiation to the overall risk, allowing us to make more accurate assessments of potential stochastic effects across the body. Now, here we see the male on the left and the female on the right, both represented as computational phantoms. These models are incredibly useful for simulating how radiation interacts with human tissues. You'll notice that different organs are highlighted in various colors. This helps us distinguish them clearly. For example, the breast, bones, colon, eyes, lung, liver, pancreas, small intestine, stomach, teeth, thyroid, and urinary bladder are all color-coded for easy identification. Additionally, muscle and adipose tissue are shown as transparent, which allows us to focus on the organs of interest without visual clutter. This detailed visualization is essential for understanding organ-specific dose calculations and assessing radiation risk. Overall, these phantoms serve as vital tools in medical physics and radiological research, helping us improve both safety and treatment efficacy. Let's look at the ICRP recommendation from 2007, which is Update 103. When we consider different types of radiation, gamma rays, X-rays, beta particles, and muons all have a weighting factor of 1. This means that their biological impact is used as a baseline for comparison. On the other hand, alpha particles, fission fragments, and heavy ions are assigned a much higher weighting factor, around 20. This reflects their greater potential to cause biological damage per unit of energy absorbed. Neutrons are a bit more complex. Their radiation weighting factor isn't fixed. Instead, it varies continuously depending on the energy of the neutrons. So, the biological effect depends significantly on the specific energy level of the neutrons involved. Additionally, protons and charged pions are assigned a weighting factor of 2, indicating they are more damaging than gamma rays or X-rays, but less so than alpha particles. All of these weighting factors are part of the broader concept called radiation weighting factors, or WR. These factors help us quantify and compare the relative biological effectiveness of different types of radiation, which is essential for dose assessment and protection strategies. So, in summary, understanding these factors allows us to better evaluate the potential health risks associated with various radiation exposures, tying back into our overall theme of radiation safety and protection. When we look at neutrons, their biological effectiveness following external exposure is reflected in what we call the radiation weighting factors, or WR. This essentially tells us how damaging neutrons can be compared to other types of radiation. Now, it's important to understand that the biological impact of neutrons on the human body varies quite a bit depending on their energy level. What's particularly interesting here is how our latest data has evolved from previous publications. For instance, compared to publication 60, we've observed a decrease in the WR for low-energy neutrons. This change accounts for the fact that secondary photons, those are the gamma rays produced when neutrons interact with matter, contribute significantly to the absorbed dose in the body at these lower energies. Additionally, for neutrons with energies above 100 MeV, we've also seen a decrease in the WR, or the weighting factor. This reflects our improved understanding of their biological effects at these very high energies. Overall, these adjustments help us better estimate the true biological risks associated with neutron exposure, which is crucial for radiation protection and safety measures. It all ties back to our goal of accurately assessing and managing radiation risks in various environments. For neutrons, the radiation weighting factor, or WR, is actually a continuous function. Unlike some other types of radiation that might be modeled with step functions, neutrons are different. This means that their WR value doesn't jump suddenly at certain energies. Instead, it gradually changes across the energy spectrum. Specifically, for low-energy neutrons, those under about 10 keV, the WR is roughly halved compared to some baseline. And for very high-energy neutrons, those above 100 MeV, the WR also drops to around 2.5. This reflects how the biological impact of neutrons varies depending on their energy. Understanding this helps us see why neutrons are treated differently in radiation protection. Their biological effectiveness isn't constant. It depends on their energy, which is why the WR is modeled as a continuous function. This concept fits into the broader theme of accurately assessing radiation risk and ensuring proper safety measures across different radiation types and energies. Let's take a closer look at some key aspects of neutron interactions with tissue. First, as the neutron energy decreases, the production of secondary photons through neutron absorption actually increases. This means that lower energy neutrons tend to generate more secondary gamma radiation, which is important when considering radiation dose and tissue damage. Next, when we talk about recoil protons, their energy tends to increase as the energy of the incident neutron rises. Essentially, higher energy neutrons transfer more energy to protons during collisions, which can lead to more significant localized damage. Moving on, at even higher neutron energies, we see the release of heavier charged particles, not just protons. These particles can cause more complex and dense ionization events, further impacting tissue response. And finally, at very high neutron energies, nuclear spallation processes come into play. These are reactions where the nucleus breaks apart, producing a variety of secondary particles. All these factors, secondary photons, recoil protons, heavier charged particles, and spallation products, are crucial for understanding neutron radiation weighting factors, or WR, and how we assess the biological impact of different neutron energies. This ties directly into our overall goal of accurately evaluating radiation risks and optimizing protection strategies. Let's talk about the hazards associated with alpha particles, specifically from internal exposures. These hazards mainly come from inhaling radon progeny or ingesting alpha-emitting radionuclides, such as isotopes of plutonium, polonium, radium, thorium, and uranium. When these substances enter the body, they can cause damage at a cellular level, which is why understanding their risks is so important. We gather information on these risks from epidemiological studies, which look at human populations, as well as from animal studies. Both types of data help us understand the potential health impacts of incorporated alpha emitters. Now, regarding the radiation weighting factor for alpha particles, recent research hasn't provided strong evidence to change the existing value. Therefore, the value of 20, which was adopted in publication 60 by the ICRP back in 1991, remains the standard. This factor is crucial because it helps us quantify the biological impact of alpha radiation relative to other types of radiation, ensuring our safety standards are based on the best available evidence. So, in summary, alpha particles pose significant internal hazards, but our current weighting factor appropriately reflects their potential risk, maintaining consistency in radiation protection. Doses from fission fragments play a crucial role in internal dosimetry because they contribute significantly to the overall radiation dose received by tissues. Their radiation weighting factor, or WR, is similar to that of alpha particles, which are known for their high ionizing power. The reason for this similarity lies in the fact that both fission fragments and alpha particles have very short ranges within organs and tissues, meaning they deposit their energy over a very small distance. This results in a high density of ionization, which in turn greatly influences their relative biological effectiveness, or RBE. Because of these properties, a WR of 20 is recommended for fission fragments, aligning with the value used for alpha particles. This helps ensure that the biological impact of these heavy ions is accurately accounted for in radiation protection and dosimetry calculations. Overall, understanding the behavior of fission fragments and assigning an appropriate WR is key to managing internal radiation exposure effectively. Heavy ions are encountered in external radiation fields, particularly in aviation at high altitudes and during space exploration. These particles can pose significant radiation risks, but it's important to note that data on their relative biological effectiveness, or RBE, are quite limited. Most of what we know comes from in vitro experiments, which means studies done outside of a living organism. As these heavy charged particles travel through the human body, their radiation quality changes quite a bit along their track. They can become more or less damaging depending on the point you're looking at. This variability makes it challenging to assign a single, definitive RBE value for all situations. In fact, for simplicity and safety, a conservative approach is often taken. We use a radiation weighting factor, or WR, of 20 for all types and energies of heavy charged particles. This is a cautious estimate, meant to ensure protection even in worst-case scenarios, and it's generally recommended for use in radiological protection to keep exposure risks as low as reasonably achievable. So, understanding and applying this WR value helps us manage the risks associated with heavy ion radiation in these high-altitude and space environments, aligning with our overall goal of ensuring safety in radiation exposure scenarios. Let's take a closer look at these tissue and organ weighting factors. These numbers represent the relative importance of different tissues in terms of radiation absorption and risk assessment. For instance, the liver, esophagus, and thyroid all have a weighting factor of 0.04, indicating a moderate contribution to overall dose considerations. In contrast, tissues like the gonads, red bone marrow, colon, lung, stomach, and breast each have a higher weighting factor of 0.12. This suggests they are more sensitive or significant when evaluating radiation exposure risks. The remainder category, with a value of 0.12, covers tissues not specifically listed here, emphasizing that many tissues contribute to the overall risk profile. Understanding these factors helps us estimate the potential biological effects of radiation exposure across different tissues, which is essential for developing safety standards and treatment plans. Overall, these weighting factors are a key part of how we assess and compare risks in radiation protection and medical applications. Let's take a closer look at some of the key organs and tissues we need to consider in our analysis. Starting with the prostate, which is a crucial gland in the male reproductive system, and then moving to the spleen, an important organ for immune function and blood filtration. The thymus plays a vital role during early life in T-cell development, while the uterus is central to female reproductive health. Next, we have muscle tissue, which makes up a significant portion of the body's mass, and the oral mucosa, which lines our mouth and is vital for protection and sensation. The pancreas is not only essential for digestion, but also for insulin production, and the adrenals, or adrenal glands, produce hormones that regulate stress and metabolism. Moving beyond the thoracic cavity, we have the extrathoracic region, which includes organs outside the chest, such as the gallbladder, responsible for bile storage, and the heart, the powerhouse of our circulatory system. The kidneys are critical for filtering blood and maintaining fluid balance. Lymphatic nodes form part of our immune system, helping fight infections. The small intestine is where most nutrient absorption occurs, and understanding tissue weighting factors is essential for accurately assessing organ doses in radiation exposure. Lastly, we have the remainder organs and tissues, which include various other structures that contribute to the overall assessment of radiation dose distribution. All these organs and tissues are interconnected in our overall evaluation, emphasizing the importance of comprehensive consideration when assessing risks and impacts. Tracking these tissues helps us develop a clearer understanding of how radiation interacts with the body and informs our safety protocols. Now, let's talk about the operational quantities used in radiation protection. These are defined at a specific point within tissue or a phantom and are based on the absorbed dose, D, but with an important adjustment. We introduce the quality factor, Q, which accounts for the biological effect of the radiation. So the quantity we use is H, which equals Q times D. Q is determined by assuming that the stopping power of the charged particle in water is numerically equal to L, which is part of the Q, L versus L relationship. This way, Q reflects how the radiation's quality influences the dose, helping us better estimate potential biological damage. When we talk about dose equivalent, we're essentially combining the physical dose with the biological impact, giving us a more meaningful measure of radiation risk. This approach allows us to connect the physical aspects of dose with their biological consequences, which is a key theme in understanding radiation protection. The protection quantities are not something we can measure directly. Instead, they are related through calculations to the actual radiation field where the exposure happens. To make this connection clearer and more practical, the ICRU has developed what are called operational quantities. These are designed specifically to help us measure exposures to external radiations more effectively. So, when we talk about operational quantities, we're referring to these standardized measurements that act as a bridge between what we want to protect and the actual radiation environment. This development is crucial because it allows us to assess and manage radiation exposure more accurately in real-world situations. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide explains that the purpose of these operational quantities is primarily to give us an estimate of the protection quantities. They also serve as calibration standards for the dose meters we use in monitoring. When it comes to external irradiation of the body, we aim to estimate a value that safely reflects the dose. The key goal here is that the operational quantity should, under certain conditions, provide a conservative estimate. That is, it should tend to overestimate the actual protection quantity. This approach ensures we're not underestimating the potential risk, which is crucial for maintaining safety. So, in summary, operational quantities are designed to help us gauge exposure accurately, while also being practical for calibration and monitoring purposes throughout the entire process. Now, let's talk about the International Commission on Radiation Unit and Measurements, or ICRU. They have established what are called operational quantities, which are essential for radiation protection. These quantities help us assess and control radiation exposure effectively. For ambient monitoring, which involves measuring radiation in the environment, we use the ambient dose equivalent, denoted as H*10. This essentially tells us the dose at a depth of 10 millimeters in a phantom representing the human body, giving us a good estimate of potential biological effects in the environment. There's also the directional dose equivalent, H0.07 omega, which considers the dose at a shallow depth of 0.07 millimeters in a specific direction, represented by omega. This is useful when the radiation source is directional or when we need to understand dose distribution in a particular direction. Moving on to personal monitoring, which focuses on individual exposure, we have the personal dose equivalent, HPD. This quantity measures the dose at a specific depth, depending on the type of radiation and the part of the body being monitored. It helps us quantify the dose someone might receive during their work or daily activities. Overall, these operational quantities are carefully defined to give us practical, standardized ways to evaluate and manage radiation risks. They connect directly to our goal of ensuring safety and protecting people from unnecessary exposure. Let's take a closer look at the ICRU sphere. This is a 30-centimeter diameter sphere made of tissue-equivalent material. The composition is quite specific, about 76.2% oxygen, 11.1% carbon, 10.1% hydrogen, and 2.6% nitrogen, with a density of 1 gram per cubic centimeter. Its purpose is quite practical. When it comes to radiation monitoring, this sphere is used because it effectively approximates the human body in terms of how radiation is attenuated and scattered. This makes the ICRU sphere a valuable tool for defining the operational quantities we use in radiation protection. These include H*10, which is a dose-equivalent quantity, H, 0, 0.7, omega, and HP, D, which refers to the personal dose equivalent at a specific depth. By using the ICRU sphere, we can standardize measurements and ensure consistency across different scenarios. In essence, the ICRU sphere helps us translate measurements from the environment into meaningful assessments of dose and risk, aligning our monitoring efforts with how the human body actually responds to radiation. Now let's talk about HPD, which stands for personal dose equivalent. This is essentially the equivalent dose at a specific depth, D, within soft tissue, measured below a certain point on the body. It helps us understand how much radiation dose a person actually receives in different tissues. For penetrating radiation, such as photons with energies greater than 15 keV, we consider a depth of 10 millimeters. This depth represents the tissue layer where the dose is most relevant for assessing risks from more penetrating radiation sources. In the case of low penetrating radiation, like certain types of scattered or surface-level radiation, we measure the dose at shallower depths. For instance, in the lens of the eye, which is quite sensitive, we look at a depth of just 3 millimeters. And for skin exposure, where the radiation primarily affects the surface, we measure at about 0.07 millimeters. These different depths are important because they allow us to evaluate the dose received by specific tissues or organs depending on the type of radiation and its penetrating ability. This way, we can more accurately assess potential health effects and establish safety standards. Overall, understanding HPD helps us connect the dots between the radiation dose and the actual risk to individual tissues, which is crucial in radiation protection and ensuring safety in various environments. Today, I want to talk about the 2 operational quantities that are recommended for radiation monitoring. The first is the ambient dose equivalent, denoted as H*D. The second is the directional dose equivalent, which we write as HD omega. These quantities are chosen because they are particularly well suited for different types of radiation fields. The ambient dose equivalent, H*D, is most appropriate when dealing with strongly penetrating radiation fields. This means it gives us a good estimate of the dose from radiation that can penetrate deeply into materials, including the human body. On the other hand, the directional dose equivalent, HD omega, is more suitable for weakly penetrating radiation fields. This quantity considers the direction of the radiation, which is very useful when the radiation is less penetrating and the directionality matters for accurate monitoring. In the context of area monitoring, understanding these 2 quantities helps us select the right measurement approach based on the radiation type and the environmental conditions. By doing so, we ensure accurate assessment of the radiation levels, which is fundamental for safety and compliance. So, to sum up, these operational quantities guide us in effectively monitoring different radiation fields, aligning our measurement strategies with the nature of the radiation we encounter. When we talk about the ambient dose equivalent, H*D, we're referring to the dose that would be produced at a specific point in a radiation field if we consider an expanded and aligned version of that field within the ICRU sphere. Basically, it's a way to quantify the radiation dose in a way that accounts for the field's orientation and the type of radiation. The key here is the depth, D, which is measured along the radius opposite to the direction of the aligned field. For strongly penetrating radiation, like gamma rays or high-energy particles, the recommended depth is 10 millimeters. This allows us to standardize dose measurements for such penetrating radiation. Now, moving on to the directional dose equivalent, HD omega. This concept is similar but focuses on the dose from a specific direction, indicated by omega. So, instead of considering the entire field, we're looking at the dose that would be produced in that particular direction if the field were expanded in the ICRU sphere. And for weakly penetrating radiation, such as beta particles, the recommended depth is much shallower, just 0.07 millimeters, because these types of radiation don't penetrate as deeply. Both these concepts, ambient and directional dose equivalence, are crucial because they help us understand and quantify radiation doses in different scenarios, depending on the type of radiation and the direction from which it comes. This understanding is fundamental for assessing exposure risks accurately and ensuring proper safety measures in radiation environments. Now, let's look at area monitoring for penetrating radiation. The key quantity here is H*10, which stands for the ambient dose equivalent at a specific point in a radiation field. This represents the dose equivalent that would be produced by an expanded and aligned version of the radiation field inside an ICRU sphere, measured at a depth of 10 millimeters along the radius vector opposite to the direction of the radiation. Essentially, it's a way to gauge the potential dose to a person standing in that field, accounting for how penetrating the radiation is. Next, for low penetrating radiation, we have H007 omega. This is called the directional dose equivalent at a point in the field. It measures the dose that would be produced at a shallow depth of just 0.07 millimeters inside the ICRU sphere, along a specific direction, indicated by omega. This helps us understand the dose from radiation that doesn't penetrate deeply, which is important for fields with more superficial interactions. Finally, these concepts tie into the operational quantities used for area monitoring. They are essential because they help us assess and control radiation exposure in various environments, ensuring safety and compliance with regulations. Understanding these quantities allows us to choose the right detectors and measurement strategies depending on whether we're dealing with penetrating or low penetrating radiation. Let's take a closer look at the concept of an expanded field. When we talk about the actual field, we're referring to the real radiation distribution at a specific point. Now, the hypothetical field is a bit more abstract. It's defined as having the same spectral and angular fluence as the actual field, but crucially, this similarity holds at all points within a sufficiently large volume. In other words, the hypothetical field is a kind of idealized or extended version of the actual one, designed to match its properties over a broader area. This idea is key when we're analyzing or modeling radiation because it allows us to make certain approximations and assumptions. Finally, the term expanded radiation field captures this broader, more comprehensive view of the radiation. It's a way to understand and quantify how the radiation behaves over a larger space, which is especially useful when we're dealing with complex dose calculations or treatment planning. So, in essence, by comparing the actual field to this hypothetical, expanded field, we gain valuable insights into the overall behavior of the radiation, helping us optimize and improve our approaches. The expanded radiation field is designed to ensure that the entire ICRU sphere is exposed uniformly. What this means is that the sphere receives a consistent radiation field, with the same fluence, energy distribution, and direction distribution as the actual radiation field at the specific point we're interested in. By expanding the field in this way, we can better simulate and analyze the radiation environment, making our measurements more accurate and representative of real conditions. This approach is crucial because it helps us achieve a homogeneous exposure, which is essential for precise dosimetry and radiation quality assessments. Overall, the expanded field concept allows us to mimic the real radiation field more effectively, providing a reliable basis for our evaluations. Now, let's take a look at the concept of an expanded and aligned radiation field. This refers to a situation where we consider a larger area of exposure, but we still assume that the radiation's angular distribution is unidirectional. In other words, even though the field is expanded, the radiation is still predominantly coming from one main direction, which simplifies how we analyze and measure it. This idea is important because it allows us to better understand and quantify radiation exposure over larger areas without losing sight of the directional characteristics. Moving on to operational quantities, these are the practical measures we use in the field. They help us assess and control radiation exposure in real-world scenarios, ensuring safety and compliance. So, when we talk about expanded and aligned fields along with operational quantities, we're essentially bridging the gap between theoretical understanding and practical application. This ensures that we can accurately evaluate and manage radiation risks in various environments. Now, let's focus on the concept of an expanded and aligned radiation field. In this scenario, the ICRU sphere is irradiated uniformly from a single direction. This means that the radiation is coming in from one specific angle, creating a consistent and homogeneous exposure across the sphere. The key here is the fluence, which we obtain by integrating the differential angular fluence over all directions at the point of interest. Essentially, we're summing up the radiation coming from every possible angle to get a total measure. What's particularly interesting is that under these conditions, the dose equivalent at any point inside the ICRU sphere does not depend on how the radiation is distributed angularly in the real field. So, whether the radiation is coming predominantly from one direction or more evenly spread, the dose equivalent inside the sphere remains the same. This highlights the importance of the expanded and aligned field in simplifying dose calculations and helps us understand how operational quantities are defined and used in radiation protection. Thank you so much for your attention today. I truly appreciate your time and engagement. I hope the insights we've shared have been valuable and have helped clarify the key points of our presentation. Remember, the ideas and strategies we've discussed are meant to support your success and inspire further innovation. If you have any questions or want to explore these topics more deeply, please feel free to reach out. Once again, thank you for being part of this journey. I look forward to seeing how you apply what you've learned.